Hello everyone! In this video, we'll start making the classic x86 assembly game of Pong for the IBM PC XT. That begins before the BIOS has even finished loading. That's right, before the system even tries to boot. I guess we can call it a kind of Pong cartridge for the PC XT. I'll take you through getting code onto this old motherboard even with no hard disk or floppy drive and get started with the programming tools needed for a good game of Pong. Pong really was a hit right from the beginning in the 70s, and if we take Futurama's word for it, people and mutants will still be playing it in 1,000 years. But I'm getting ahead of myself. In the first video of this series, we fixed up this IBM PC XT motherboard from 1984 by diagnosing a bad power rail, fixing a ROM chip, and finally got it to post. In the second video, we successfully added a VGA graphics card and then used a microcontroller as an active adapter to let us connect a modern PS2 via USB keyboard to the DIN5 connector on the motherboard and fixed up some code to convert from 11-bit PS2 codes to 10-bit PC XT scan codes. Before we left off, we had some fun playing with the built-in cassette BASIC included with the BIOS ROM and comparing it a bit to BASIC on the 6502. In this video though, we'll leave BASIC behind for now and see if we can't get the motherboard here to run some 8086 assembly code of some sort. Since we still don't have a hard disk, floppy drive, or even controller cards for them, and we haven't used some sort of modern hack, we'll need to get a bit creative if we want to run some code besides BASIC. Luckily, I have this old 10base2 network card that I have a vague memory of using to play Doom over LAN with my classmates back in 1998. What's that got to do with this old motherboard, you might ask? Am I going to boot the machine over a coax cable? Well, no, not exactly. I don't have another computer with a 10base2 card, and even if I did, we'd need a special ROM on the card to boot via the network. But you might have guessed I just gave away the trick. Since basically all ISA network cards came with a socket for a ROM to configure the card for the system or to hold the configuration to boot from LAN, we can take advantage of this ROM socket to hold our code, even if it doesn't have anything at all to do with the card it's seated on. Since you saw the card in the last video, I chose to replace the 10 microfarad electrolytic capacitors since they all looked visibly bad and, like it was common in the 90s, I had to place some jumpers to configure the card. I couldn't find anything at all about the card itself online. It has a Realtek 8009 IC that I couldn't find a datasheet for, but at least the datasheet for the big brother 8019 was a bit helpful. But mostly I just had to rely on the partially obscured silkscreen markings. Even though the ROM chip I have here, a Winbond W27C512, probably started its service life with a similar task to this, I have a feeling it might be a bit big. But maybe it'll just work. Before we spend too much time writing code, we probably want to make sure it actually works. So let's see if we can't make the simplest possible assembly program to tell us if the idea about using the card works. I use NetWide Assembler or NASM for this, but you'll probably have similar results with FASM or something else. I just open a text document and start typing. So assembly language is easy that way. First, I specify that I would like the assembler to complain if I use opcodes that don't work on the 8086 or 8088. CPU 8086. Considering we're going for the absolute basics and NASM doesn't care if we just start writing code without worrying about segments and stuff, we can get right to it. Lucky for us, the BIOS has a built-in interrupt routine to print a character at the current cursor position, and that should be enough for us to determine if the ROM code is executed or not. The IBM Technical Reference Manual holds all the answers to how this works, though the documentation is a bit hidden away in the source code in section 562, page 210 in the PDF I have here. So we move 0A into the AH register, and then we can move our character into the AL register and then simply call int 10 hex. So far, so good. That should print an exclamation mark, and I'm sure this code would assemble just fine. But how does the PC actually know to start loading extra code from a ROM? Since there is no real difference between random floating states of the data lines and a ROM in a socket, to the CPU anyway, What stops it from trying to execute random data, and what makes it try to run our new code? The manual also has a section called Adapter Cards with System Accessible ROM Modules in section 510, page 158. That explains how this works. The BIOS scans addresses C8000 through F4000 in 2K increments for a magic word of AA55, and if it finds it, it computes a checksum by summing each byte in the number of 512 byte blocks defined in the third byte and does a modulo 100 hex. Said another way, it checks if the remainder of dividing the sum of every byte by 100 hex is 0. If it's valid, the code is executed. If not, it's ignored. But if only the checksum is invalid, it will print an error. We can add the magic word and the block size at the current positions by putting them above our code. Since the checksum depends on the sum of all our code, we'll have to compute that afterwards. Since the manual specifies we are executing this code with a var call, we just need to add a var return to the end of our code. I arbitrarily chose 16K for the size of our ROM. Since we need to calculate the checksum, we need to make sure the unused part is filled with a known value. The NASM macro times will let us fill the rest. Now we can compile our code with NASM hello world. And I like to take a look at the code using XXD. Since our code is only 10 bytes long, including the magic word and length byte, and the rest is zeroed out, it's a simple matter to calculate the checksum and fix it. We can just grab our programmer's calculator, add up all the hex values, and check the remainder. Modulo 100 hex is the same as ending with FF hex, which gets us 56 hex, our current checksum. To correct our checksum to 0 hex, we can just add a byte somewhere after our code with the negated checksum. Said another way, we can take an 8-bit 2's complement, or said a third way, 100 hex minus 56 hex is AA hex. Let's add that to our code and do a final check to make sure the checksum is 0 like it's supposed to be. Of course, manually summing bytes to calculate the checksum gets old fast. We could write a script to do it automatically, but lucky for us, Sergey Kiselev already wrote a tool for this purpose in C as part of his floppy BIOS, which is only a git clone and a makeaway. We should probably take a look at that sooner rather than later. Since the checksum is now correct, the BIOS should execute the code successfully, so let's burn a ROM using MiniPro and our trusty TL866 and try that out. As you might have noticed and appreciate, I speed up these sections of the video as programming these old EEPROMs takes quite a while, since it has to write the whole chip even though our code is only 10 bytes. If you're curious, it takes about 30 seconds to program the EEPROM, and the XT RAM check takes about 50 seconds. Finally, we are ready to plug the ROM into the card and the card into the XT motherboard. Okay, no exclamation mark. That seems to indicate the BIOS didn't register the ROM. Since the code is pretty simple and I still think it should work, I'd like to verify that the address lines are decoded as expected. So let's bring out the multimeter. For instance, a 32K ROM might have the programming signal on pin 1, which is where address line 15 is located on a 64K ROM. I wouldn't recommend poking around with a multimeter with the power on, but I'm okay with the risk of letting out the magic smoke for now. Pin 1 reads a high, which might mean we're in the same situation as we were with the BIOS ROM in part 1 of this series. But let's check pin 27 as well, since that is where a 14 should be. Okay, that's high too. I guess that could make sense if the board only supports 16K ROMs, but since we're reading high on every pin so far, let's keep checking address pins to see if they make sense. Okay, so A13 and A12 both read low, so I think we can assume the board here assumes we're using a 16K ROM and always pulls pin 1 and 27 high. That's fine as long as we're okay only using a quarter of our 64K ROM, since we can just place our code at the offset where both A15 and A14 are high, which decodes to the address C000 hex. Since our code is already only 16K, we just have to place it at the right ROM address. We could do this by cloning our 16K ROM 4 times in a row on the same ROM, kinda like we did with the 32K ROM in part 1, but this time I'd like to fill the rest of the ROM with zeros instead. We could have the assembler fill the start of the code with 48K worth of zeros, but I'd actually like to use a different approach this time. Using dd and cat, we can easily make a block of zeros to put in front of our code, so let's try that. You might know dd if you ever tried cloning a disk image to a floppy, USB stick, or SD card, but it'll let us use basically anything as the input. So if we just use dev0 as the input device, specify our block size as 1024, and put however many blocks we want in the count, we'll get a file we can use to prepend our code ROM. After creating this padding file, we can simply use cat to concatenate the 48K padding and the 16K code ROM to make a full 64K ROM with the code at the correct offset. Oh, wait a minute. A 64K ROM should be 65,536 bytes long, and that's not exactly what we're seeing here. The 16K code ROM should be 16,384 bytes, but it's a bit bigger than that, so it looks like I messed up filling the code ROM with zeros. Yeah, I did. The $sign is a shorthand for the current address, and $$ is shorthand for the beginning of the current section. And it looks like I have them reversed, if I want to get the length of the code. Easy fix. Technically, it wouldn't have made any difference since too many nulls wouldn't have changed the checksum, but now that we moved it to the end of the ROM by prepending 48K of null bytes, MiniPro would have given us an error that the file won't fit in a 64K ROM. After that little fix, we just reassemble the code with NASM, cat it with the 48K file, and finally burn the ROM again. Let's see if that didn't make a difference. Oh, that was weird. Did you catch it? First of all, we didn't get the exclamation mark like we wanted, but secondly, there was only a single beep. Usually we get 2 beeps when there's a floppy controller error like 601. Let's try a Control-Alt-Delete and see what we get after a warm restart. Okay, 2 beeps. Nothing to see here, I guess. I really have no idea what's going on here. Maybe that single beep meant something, maybe it didn't. I guess we can try reseating the ROM. But that did absolutely nothing. Let's take a look at the code and see if we can't figure it out. I think I have an idea of what it might be. The print character function 0A in the 10 hex BIOS interrupt call doesn't just take the character as a parameter, it also takes the page number in BH, which is probably 0 like it should be, and then my mistake. It also takes the number of times to print the character in CX, which means a 0 in CX wouldn't print anything. Let's see if this didn't finally get our code working. Since we changed the code this time around, and I'm officially done, summing bytes manually, I think it's time we get the tool I mentioned earlier from GitHub. It doesn't have any special dependencies, at least nothing Homebrew can't handle. Link in the description, of course. The tool simply takes input and output file, start and end locations of the ROM in hex, and a hex location inside the file to put the checksum fix. If we keep adding build steps like this, I guess we'll eventually need a build script. But now I just hope we can get it to work. Let's cat and burn the ROM again and see. Ah, finally. Our assembly code has tamed the ancient beast and made it do our bidding. Since we now know a relatively easy way to get code onto an XT with no drives, we can finally get started with what we set out to do, writing a game of x86 assembly Pong. If you'd like to see how we get from here to a working game of Pong, though, you'll have to wait a little bit, since it already took a good chunk out of my free time this last month to make this video into what it is now. So, rather than waiting to publish an hour-long video, you get this part now, and most of the Pong coding will happen in part 4. I hope you'll stay around for that part too. Pretty soon after that, you can also expect to see an update to my 6502 single breadboard computer project, since that desperately needs a display of some sort. But for now, thanks for watching.